Yeah, I addressed any concerns you guys had, any mistakes you guys may have made. I don't know, was Google Forms glitchy?
I thought it was glitchy first because all the numbers weren't in order.
Oh, no, I made it so it shuffled everything.
I was like, what is that? It's just
Yeah, no, that was just confusing.
I was gonna be like, sir, everything's not in order. Is everything already?
Everything's
And some
good.
of some of the options, it was like, it was obviously A, B, C, and D, and then one was like B, A, D, like C or something.
But there's one thing that just said option 1.
Oh no, that I forgot to delete that.
Oh yeah, I was like, wait, what do I do there?
Yeah. No, it didn't come from marks. That's why you didn't see like a record or like a
Yeah.
red star on it, so you didn't have to see it. So today we're gonna continue with polynomial functions. We might get to synthetic division today. You guys probably have heard about that.
I'm like log division, but worse.
No, it's easier than long division.
Okay,
Oh,
better. Okay.
better.
I never heard about it, but
So if there's if I don't say what to use on a test when it comes to synthetic or long division, always do synthetic division.
Oh.
Okay, but that only works if you have an actual real roots as these dividers. Okay,
Okay.
so I'm gonna show you what that means. So these are some functions you guys learned in grade 11. Okay, I'm pretty sure you guys are familiar with them. We have ax plus b, we have linear, we have the quadratic, ax squared plus bx plus c, you have the reciprocal 1 over x, we have our trig functions, we have our radical / square root function, and you guys have your exponential functions, okay? So when graphing any of these, okay, what I suggest you guys do when it comes to mapping notation is use the x values -2, -1, 0, 1, and 2. I'm not sure if your grade 11 teachers told you to use those points last year.
Yeah, just some of them you can.
Yeah, for trig, you can't really do it. For the square root, you can't use it because you can't have a negative square root. Okay, so this applies to most of them besides the ones I said. So the square root and the trig function, obviously the reciprocal, which x value can't you use? 0, right? Because it's just going to give you undefined, and because there's an asymptote there. Okay, so these are generally the 5 main x values I want you to plot when you're doing transformations for polynomial functions. All right. So the new functions that you guys are going to learn this year is the cubic function and the quartic function, but in standard form. Okay. So this quadratic function over here, that is called standard form, right? You guys learned that last year. How many ways can this be broken down into?
2 other different ways.
Yep.
The
Which one?
vertex form and the factored form.
Yep. So this can be broken down into vertex form and factored form. Okay. What form do you think these two can be broken down into?
Factored form.
Okay. Can we have a vertex form for them?
Wait, what's vertex one?
Vertex form is f of x is equal to a x minus h squared plus k.
Oh, okay.
Right? You guys remember that notation, right? So why can't we use vertex form to factor the cubic and quartic functions and quintic and so on?
I don't want to say they don't have a vertex.
Okay, you're technically right. They don't have a singular vertex.
Yeah, that's
They have, so those vertex in these new cubic and quartic polynomial functions, they're called turning points. Okay, so what I mean by that is we can have a graph that looks like this. Okay, we have turning point here, which can be your vertex at that point, turning point here, and turning point there. Okay, but those new vertex points are going to be called your absolute maximums or absolute minimums, or local maximums or local minimums, okay? Which we will talk about, I think, in a few lessons from now. But the only way you can factor these cubic and quartic functions is through just factored form, okay?
Do we factor by grouping?
No, you cannot factor by grouping a cubic and quartic function. This is where synthetic division and long division comes into play. So we will talk about the strategies to use to figure out how to factor these polynomial functions. So what this can end up looking like can be f of x is equal to a, let's say, minus r squared, and x or a minus, let's just say, I should use x. I don't know why I'm using r. So f of x, yep, is equal to x minus r to the power of 2, or x minus s. What do those add up to? Or what does the degree add up to still? Because remember, this is a degree of 2, and this is a degree of 1. So in total, it is a degree of 3. So it's a cubic function, okay? In terms of graphing, we're not going to get into that right now. I believe there's a later portion in the lesson that will get to that part, right? The higher the exponent gets, the more turning points you'll have in the graph, or you'll just have a bunch of points bouncing off everywhere. So now we're going to look at the properties of polynomial functions. So a polynomial function is defined by a polynomial in one variable raised to a non-negative integral. Okay, so the power has to be positive or 0, which 0 gives us a constant, basically. And the degree of the polynomial, so the degree of, which is represented by n, depends on the highest exponent of the polynomial in expanded form, okay? So, like I said, I gave you the example. Let's just say we have f of x is equal to 2x minus 3 times 2x plus 4 plus 2x minus 4, okay? So what would the degree of this polynomial be? It's an expanded form. So what would the degree be in total? 3. So the degree of this polynomial function is 3. Okay? All you're doing is adding the exponents from each bracket together. So now we're going to look at decreasing and increasing functions. So a function is increasing on an interval if the graph rises from left to right, and decreasing on an interval if the graph falls from left to right. All right? So, like I said, this over here is going to be called your turning point. Which is usually just the vertex or the vertex. So for this one, we have a straight line. Is the graph increasing or decreasing? It's increasing over all of the x values, okay? So this basically your interval of increase would be from, so basically negative infinity to positive infinity, or over all the real numbers on the x-axis, okay? Which is why you have this. How about the next one? Are we increasing or decreasing? Decreasing, so the function decreases over the x value, the x values, okay? And the last one, we have f of x is decreasing from negative infinity to 3. And then it's increasing from 3, so after a turning point, to positive infinity, okay? So usually when you have a turning point is where your intervals of increase or decrease change, okay? So just keep an eye out for that. So like I said, a turning point is where a function changes from increasing to decreasing or vice versa.
For
For the bracket, do you have to do those special brackets for when it gets to 3?
For this one,
Yeah, like the little square, like the half square one.
the square one. So the reason they put the round one is because 3 is the turning point. So it's
Okay, so you don't need to do that.
no. So when it's 3, it's basically, so the slope of that graph right there is 0. So it's not really increasing yet. It's just staying there. That's the point of reference of where it changes direction and where the points change from decreasing to increasing, which is why you just put the round bracket, right? So you don't actually include that point, because if you sub that back in, you're just going to get -2 for both cases. So you can't really include the square bracket into the interval of increase and decrease for that point.
Okay.
So we're going to get to a couple of examples. So what we want to do is be able to predict how a polynomial function will behave based on the equation alone. We do this by examining the degree, even or odd, the value positive, negative, the leading coefficient. From this information alone, we can determine the end behaviors of the graph. Okay. So when it comes to the end behaviors of the graph, when you have a even degree polynomial function, the end behaviors are going to be the same. Okay. So either both ends are going to approach positive infinity or both ends are going to approach negative infinity. All right. When you have a odd polynomial function, you're going to have one end behavior approach negative and the other one approach positive. Okay, depending on if the a value has a negative or a positive number in it, which we'll take a look at it right now. So we want to graph each of these cubic functions on different sets of axes. So we're going to use Desmos. I'm going to pull it up over here. We're going to sketch our results. So we have group A, we have y is equal to x cubed. Y is equal to x cubed plus x squared minus 4x minus 4. And then the other equation. And then for group B, we have just where A is negative. Okay, so we're going to take a look at what happens to those graphs when we have A as a positive leading coefficient and A as a negative leading coefficient. So we want to determine the end behaviors, the number of turning points, the number of x-intercepts, the value of the y-intercept, and from what quadrant it starts and what quadrant it ends off in. So we're going to start with y. Let's start with y is equal to x cubed, which is what we know. So we know y is equal to x cubed looks like this. So from what quadrant does it start and what quadrant does it finish at? Yeah, so it goes from 3 to 1. So this is quadrant 1, 2, 3, 4. How many turning points does it have? 0. This does not count as a turning point. That is known as a point of inflection, where it just changes direction slightly. It doesn't go from increasing to decreasing. Okay, remember turning points, it has to go from decreasing to increasing or vice versa. Okay, as you can see, it is increasing, increasing, increasing. It takes a turn, but it still keeps increasing. Okay, so that would not be a turning point. What is my x-intercept? Or how many x-intercepts do I have? 1. And what is my y-intercept? 0. And now we're going to take a look at y is equal to negative x cubed.
Where'd you get 1?
Oh, it's the number of x-intercepts. It's not asking us for the coordinate.
Oh, so like, how do you know it's 1?
Because we just have one part of the graph that passes through the x-axis.
Okay.
That's why we have 1. Okay. And next we have y is equal to negative x cubed. So we did this yesterday. The graph looks like this. So what quadrant did it start at and what quadrant does it finish at?
2 to 4.
2 to 4. Number of turning points, 0. Number of x-intercepts. And what is my y-intercept? 0. So now we're going to look at the next one. So we're going to look at the positive ones now. So for the next equation, we have y is equal to x3 plus x squared minus 4x minus 4. Okay? So I'm going to share this on Desmos, and we are going to graph it.
Because you don't know how to yet.
Because you would have to factor or use synthetic division to find the roots. Okay? So what we have is y is equal to x cubed plus x to the power of 2 minus 4x minus 4. So that is how the graph for group A number 2 would look like. Okay? So I'm going to go back to the notebook and I'm going to plot it. So what quadrant did it start and what quadrant did it finish in?
One to 4, or 1,
3 to 3.
So it started at 3,
my bad.
it ended up at 1. It's okay. How many turning points did we have? 2. How many x-intercepts do we have? 3. And what is our y-intercept? Remember, when we're looking at the equation, it's the last number in the equation. Nope. The last one, -4.
Oh, boy.
-4.
Oh, yeah, yeah.
Right?
I can't.
Because x has to equal 0 on each.
So if we continue the same concept, so I'm just going to roughly sketch out the next graph. So our next equation is y is equal to x3 plus 5x squared plus 3x minus 9. So based off what Desmos graphed for us for our previous equation, do you think the next one's going to look similar?
Yeah.
Yes.
It'll look similar, except obviously the x-intercepts are going to change. Okay? I'm going to try to draw it slightly differently. There we go, different x-intercepts. So what quadrant did it start in? 3, and it finished in 1. How many turning points?
2.
2. How many x-intercepts?
3.
And what is our y-intercept? -9.
Wait, so sir, are these all, like, so if it's a cubic function, is that the
Mhm.
constant term? Yeah, they all have the same. Okay, they all have the same property.
They all have the same properties, okay?
Different y-intercepts.
Just different turning points. Depending, the parent function y goes x cubed, like I said, doesn't have any turning points, and the y-intercept is 0. Okay. The number of turning points depends on how the equation looks like when it's in factored form. Okay. So the reason why this has two so there's a general rule. The number of turning points is determined by the highest exponent minus 1. So n minus 1. Okay, so our highest exponent is 3. 3 minus 1 is 2, which is why we have 2 turning points.
Oh, that's like a rule?
It's a rule.
Rule of thumb or an actual rule?
Pardon?
It's like a rule of thumb or is it an actual?
It's an actual.
rule?
So let's say I had a polynomial function with a degree of 5. What is the maximum amount of turning points I can have?
4.
5 minus 1,
Oh,
right? So 5 minus 1 is 4. But you can have 3 depending on how it's factored.
oh, so like we don't know it.
You don't know. You just know the maximum can be 4 until you actually factor it.
So it's kind of like with odd and even functions, right?
Yeah.
Okay.
So if this is how our equation with a positive a value look like, how would our negative a value equations look like? So the next one we have for our negative a's is y is equal to negative x cubed minus x squared plus 4x plus 4. So how do you think this would be graphed in?
Reverse.
Just reflected on what axis?
Okay.
X-axis. Okay, so what quadrant did it start and what quadrant did it finish in? It started at 2, it went to 4. How many turning points? 2. How many x-intercepts? And how many y, and what's our y-intercept? That looks like an ugly positive 4.
Wait, so just for clarification, so the first two that we did, they're cubic functions. What about the other?
They're cubic functions too.
Okay.
It's just this one has added variables to it, but because when we determine the degree of a polynomial expression,
Right.
it's the highest degree
Yeah.
of that
Which makes
expression.
it a cubic.
Yes.
Oh,
So what is the main difference you see between the parent function, x cubed, and the functions with the added variables
do
to
they
it?
have a turning?
They all have turning points and multiple x-intercepts, okay? So now that we figured out a general rule for the number of turning points, what do you think the general rule is for the number of x-intercepts? So we have the amount of, this one has 3, this one has 3, this one has 3, and this one has 3.
The highest exponent.
Yep, so the degree of the polynomial is the maximum amount of x-intercepts you can have, okay? So if we have a cubic function, the maximum amount we can have is 3 x-intercepts. If we have a polynomial function of degree 4, how many x-intercepts can we have? 4, so that would be the maximum.
Will that ever change to factor again?
Yes, it all depends on how it's factored.
Oh,
Okay.
Okay.
So let me just give you guys a little example. So let's just say I have f of x, and this is what it looks like in factored form. So what is our degree?
3.
No,
3.
3.
The total degree is 3, okay? How many x-intercepts would we have?
2.
2, okay? Why would it be
Wait,
2?
No, it would be.
Why would it be 2?
Oh,
the
yeah,
highest
it'd be
one is
two,
2,
the
right?
highest one's 2, yeah.
The highest one is 2, and also because when you graph that, at this x-intercept, the graph is going to have a double root because it's a, what's it called? A perfect square, whatever, because you have the 2 brackets. So it's basically a parabola that jumps at that point. So you're gonna have a double root, so which counts as just one real root.
And does that mean that one only has one turning point?
It still has 2.
Still has 2.
Yep.
So you don't have to do the minus thing?
No.
Okay.
So that one would still have 2. Like I said, we'll get more into that later with synthetic division, because after we learn about synthetic division, it becomes easier for us to graph these functions, okay? Because this is technically an x-intercept, okay? You have an x-intercept at x is equal to -1, and this is also an x-intercept at 3/2.
So for the turning point,
Mhm.
like you said, oh, just get the biggest one, take like a -1.
Yep.
So, do we have to do that for like when it's factored?
Yeah, you still do, the highest degree is 3. 3 minus 1 is still,
Oh, we
2.
take the degree, not the
Yeah.
highest exponent?
Yeah.
Okay.
Let me just erase this. And based off our previous, this last one is going to look the same as well. So it goes from quadrant 2 to quadrant 4. It has 2 turning points, 3 x-intercepts, and what is our y-intercept for that one? Positive 9. The reason why I tell you guys when we get to the division one to do synthetic division is because it saves you the trouble of going through that whole process of long division you went through in grade 5. So,
Oh, it's so long.
I think that's when you learn long division.
Think about it 7 years ago.
That for me was, I don't even want to say. How old were you guys in grade 5?
Well, 7 years ago. 10,
10?
roughly.
That was already 17 years for me? Oh, that's a long time.
Wait.
Now you're trying to calculate.
What's 10 plus 17?
7 plus 17. 26. I'm kidding. It's 27.
Yep.
You do like
I would not be a teacher at 19. That's mathematically not possible anymore.
Oh.
Well, it used to be, because people got accepted early, like back in the day where teachers college was never a thing. You could have just done their undergrad, gone through it quickly, and then just taught from the age of 19 all the way to however old they are right now. So we're gonna reflect. So which groups of graphs is similar to the graph of y is equal to x and y is equal to negative x? So is group A or B similar to y is equal to x? So we're gonna draw y is equal to x. So it goes from quadrant what?
3 to 1.
So which group, A or B, went from quadrant 3 to quadrant 1? So this is similar to group A.
Oh, no, I can see it.
And y is equal to negative x is similar to what group? B, because you go from Q2 to Q4, which means it's similar to group B. Okay, so now we're going to take a look at the even degree polynomial functions. So we have y is equal to x4 in group A and y is equal to negative x4 in group B. So we're going to be doing the same thing. So from our graphs before, what does y is equal to x to the 4 look like? Like a big, yeah, exaggerated U. And what quadrant does it start and what quadrant does it finish at?
2 and 4.
No, 2 to 1.
2 and 1.
Remember 1, 2, 3, 4.
Yeah.
Goes from 2 to 1. How many turning points? 1. How many x-intercepts? 1. And what is our y-intercept? 0.
Sorry, but it's on the X and I. How is it only one?
Oh, when with x to the 4, it looks like it's touching the x-axis all the time, but it's really just close to 0.
Oh, okay.
It
So
just
it's
has
just approaching.
one
Oh,
vertex.
okay. That's- I don't know how to feel about that.
And then y equals x to the negative 4, what would that look like? Yep. So what quadrant does it start and what quadrant do we finish at?
3 and then 4.
Yep, 3, 4. Turning points,
1,
1, x-intercepts,
1,
and y-intercept,
0.
0. Okay.
I hate these glasses.
So now we're going to look at the other equations. So what did you notice about the end behaviors with the odd degree functions? Were they the same or different? Or was one approaching negative infinity while the other side was approaching positive infinity? Yep. So, so for the positive odd degree functions, as x approaches negative infinity, y approaches positive infinity. And on the positive side, as x approaches positive infinity, y approaches positive infinity. Okay? And when you change that positive a to negative, it just flips. Okay? So, and we're going to discuss that as we go on.
Can
Yes.
you write out what you did then?
Sure. I'll just write it on the page. So, end behaviors for odd degree. So when we have a positive leading coefficient, this is our end behavior. So as x approaches negative infinity, y approaches positive infinity, and as x approaches, what am I doing? That was bad. So when we have a positive leading coefficient, so that means our a is positive for odd degree polynomial functions, as x approaches negative infinity, y approaches negative infinity, and as x approaches positive infinity, y approaches positive infinity.
That's for other days. Yeah, but he's writing it down. That would be.
So this would be a positive leading coefficient, y is equal to x cubed. And when we have a negative leading coefficient, it is just the opposite for the y approaching part. So as x approaches negative infinity, y approaches positive infinity, and as x approaches positive infinity, y approaches negative infinity. And an example of that would be y is equal to negative x cubed, because our leading coefficient is negative 1.
Leading coefficient. The A value.
So this is your a value. I don't get why these things don't have default to the skinniest line possible.
Because you have to manually do it.
For the first one, it would be linear as well, like as an example, right?
No, this is a cubic, x cubed.
I know, but like with the end behaviors. the end
Oh, yeah,
behavior-
for linear, yeah.
Okay,
Because linear is odd.
yeah, okay,
That's fine.
that's making sure.
Everyone copy this down. So we're gonna go back to our examples. Okay, so when we have an even degree polynomial function, where would our quadrants start and where would we end up in from what we did already?
Positive one.
Starts at 2, ends off in 1. And for our even degree polynomial functions with a negative a, what quadrant do we start in and what quadrant do we finish in? 3 and 4. Okay. Now, this is where the number of x-intercepts differ, okay? So I'm going to show you 2 of them that have different amounts of x-intercepts based off the graph, okay? So how many turning points would this equation have? Three. What is our y-intercept? It's the last number.
Yeah.
And how many x-intercepts would we have?
4.
4. How many else? Remember, it depends on how it's factored. That's what I'm going to show you how this graph is, okay?
Oh, that's a good question.
Will we have to graph it first to know how many turning points are, or is it just like a set rule? Like you have to-
No, we can graph it first. So actually, when I give you these questions, I'm going to have the graph already for you. This one, I just have to put it on decimals to show you how many
Okay,
turning points there are.
so, cause like, I'm just wondering, like, is it like a set rule?
Generally, there is most of the time n minus 1 turning points.
Okay,
Like 99% of the time, there's n minus 1 turning points.
So like turning point is like clarify, it's like 4 minus.
Yep. So turning points is n minus 1. So n is the degree of the exponent.
But that isn't always the case.
You said it's 99.
99.9.
And you give us the graph, so just look at it.
Okay.
So like how does this work for like the example I did like before is there's like 2x minus 3 like all brackets like squared.
Yeah.
Oh, that one? The example I gave you guys?
The one that, yeah, don't do
So just repeat the equation because I probably forgot it.
2 like bracket and 2x minus 3 close bracket to power of 2 and then open bracket x plus 1 close bracket.
So that's still 2 because there's 2, right? So it's
Okay,
still
so-
I is 3.
Let's start it out. What would our x-intercepts be at?
Minus 1 and 3.
Uh,
Wait, no, it's
3
3
over
over 2.
2.
3 over 2, so that's 1.5, right?
Yeah.
So let's just say it's here. I'm just rough sketching it because I don't want to put all the values. So is our leading coefficient going to be positive if we expand all that? Yes.
Yes.
Because there's no negative where the x's are. So positive odd degree polynomials start at quadrant 3 and end at quadrant 1, okay? So, 3 and 4 are 1 and 2 and 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 3 and 4 are 1 and 2 when we're graphing this, which we're gonna learn later, at this x-intercept, okay? So over here, it's just gonna bounce off of it, okay? So I'm gonna show you what I mean. So how many turning points would we have in this case? 2. Okay? And this, the reason why we have 2 is because of this bounce over here, okay? And I'm gonna just briefly go through it now, but more detail will come later because there's a separate lesson on that. So this is a bounce off at that x-intercept, okay? So it turns into a parabola. This just goes through the x-intercept. If I had a degree of 3, how do you think it would look like? Yeah, it would just inflect at that point, okay? So it wouldn't actually count as a turning point because this is not a turning point, okay? So, like I said, the turning point depends on how it's factored, okay? If you have just, if this was just x minus 3, 2x minus 3 times 2x plus 3 times x plus 1, then you would probably have still 2 turning points, okay? So as you can see, we have a degree of 3, n minus 1 is 2, so we still have 2 turning points, okay? All these brackets mean is how the graph is going to react at that x-intercept, okay?
Right.
So remember, a degree of 1 we associate with linear, so as you can see, that's why it went straight through, okay? A degree of 2 we associate with what graph? A quadratic, which represents a parabola, okay? Which means it just bounces off and makes a U shape at that x-intercept. And a degree of 3 we associate with what type of graph? Cubic, which if we ever had a degree of 3 with a bracket, it would just be a change in direction slightly, or change of inflection, okay? And if we have x to the power of 4, we still have a parabola-like shape, except it's just a wider base. That's all it is. But like I said, we will have more practice with that. I just want to show you guys how the end behaviors react with even degree polynomial functions right now. So I'm going to graph this next one on Desmos. I'm going to stop presenting. So we have our even polynomial function, which is x to the 4 minus x to the power of 3 minus 6x to the power of 2 plus 4x plus 8. So how many turning points does that graph have if we take the n minus 1 rule? 3. 1, 2, 3. Okay? And what do you notice about the end behaviors of the even degree polynomial function with a positive leading coefficient? They're the same, right? So they all approach what? Positive or negative infinity? Positive infinity.
No, I'm thinking, I'm kind of weird. But don't they technically approach both because it's going both ways?
Yeah, that's what it's saying.
Yeah. Huh?
Have you read that?
The end behavior?
Yeah.
It's just,
So how many x-intercepts do we have in this case?
Oh, sorry, 1, 2, 3, 4. I
smooth.
was thinking about something else.
So you were wrong, like X, arrow, and then.
Right? And so generally, generally speaking, how many x-intercepts would we have in general if we had a degree of 4? What's the maximum amount? 4. Okay, so we can safely assume that this also has 3 turning points, 4 x-intercepts, and what's the y-intercept on this one? -4. But I'm just gonna repeat again. What does the x-intercept depend on? The amount. I gave you an example already.
The highest degree.
The highest degree when it's
Factored.
factored. Okay.
After.
So the number of x-intercepts is dependent on how it transforms from standard into factored form
So you basically get all the information except for the x-intercept.
until you graph it.
So there's always gonna be a graph.
There's always going to be a graph.
Okay.
Unless I have a question where I give you the expression in standard form and say, this is a factor, use synthetic division to graph the functions.
Okay.
No, it's thinking we don't use transformation maps to go.
For graph sketching, like this, we don't need transformation maps. Because we just go based off the y-intercept, the x-intercepts, the way it's opening, and the rule of n-1 turning points.
But if we're actually like plotting and making graphs, we can still use transformation? Or
Uh,
is it just using synthetic?
An example of a question I would give or I've given would be to prove that this point exists in this graph. That would
Those
be
are like
the
the
question.
technical questions that you give a point and then like prove that it's.
Like a,
But you would just use it in factored, put it in factored form first, and just sub in that x value to determine if that y value exists in that function. So let's just say it asks prove the point 46 is an actual point on the function y is equal to x cubed minus 6x squared plus 3x minus 1. You would factor it first, okay? Or you can just simply plug in that x value right away and just see if it gives you back 6 as the y value. So that is how you would approach that question. So how many turning points would this have? We can assume
3,
3 x-intercepts.
4.
And what is our y-intercept for that one? 10. Okay, so again, 3, 4, and our y-intercept is positive 4. So if this is a degree of 4, and with a positive leading coefficient, it looks like this, what would a negative leading coefficient look like with a degree of 4?
reflective.
Yep. So these ones, the end behaviors are the same, okay? So for a positive leading coefficient in an even function, so as x approaches negative infinity, y approaches what? What does y approach?
Positive.
Positive infinity. And as x approaches positive infinity, y approaches positive infinity. Okay? And when you have a negative leading coefficient for an even degree polynomial function, you're just approaching negative infinity all the time.
Right.
Wait, sir.
Yeah.
You put positive infinity.
Oh, yeah, my bad. Thank you, Yusuf. If I make mistakes, just call me out. I'm not gonna get my feelings hurt by you guys.
I feel like some of us are just scared to point it out because I feel like you're
Why?
right.
Because I'm gonna be like, oh, no.
No,
you're
if
not.
we think you're right, and then if we correct you, and then it's wrong, it'll be just embarrassing for us.
What?
But that's only if I make it a big deal and be like, you're wrong. I don't know where you saw a mistake from.
I know, dude. I don't have that much self-confidence.
Anything.
Yeah, that's
Feels so tough. Feels bad.
Okay, so Now, what group of graphs, based off the ones we had, group A and B, which one is similar to y is equal to x? Group A or group B? X squared, sorry.
Okay.
Group A. Which means negative x squared is more relatable to what? Group B. I'm telling you guys, 70% of the advanced functions course is just graphing.
That's pretty chill.
Wait, sir, could you scroll up again?
Yeah.
I just want to copy it down again.
What about calculus?
No, it's mostly graphing too.
Questions can take like a whole page from what I've seen, like for calculus.
Yeah, depending.
And if
And
you
then,
make a
and then you
mistake,
get to your undergrad, and then they make the question worth 2 marks, and you're like, this is all the work I did, and it's only 2 marks. That's what happens.
yeah, because like in calc, what was it? Like you have to find not the derivative, but you also have to graph it, and then you have to double check that your points are correct, I think, right? And that just takes up like a page and a half. And if you make a mistake on your first out of one, you make a mistake on the
Depending
whole.
on the school you go to, part marks is either existence or non-existent. So that's why I said UTM is,
Yeah, because I think UTM doesn't give you front marks. Cool.
That's brutal.
some profs actually make the multiple choice worth a negative mark. So if you answer wrong, you get a negative mark.
What?
There's no way.
So the option is, you get it right, you get +1. You don't answer it, you don't get a mark, so you get a 0. Or if you get it wrong, you get a -1.
So it's better for you to not answer.
If you don't know it, you might as well just leave it not answered at all. Save you that negative mark.
Or my brother's gonna have such a difficult time.
And some profs actually take a mark off if you know what you're doing.
Don't let the teachers do that for jokes.
That's for UTM. They're a strict school.
See, but why though? Like, it's UTM. It's nothing too special.
It's the U of T label they have. That's fine.
But it's not even like that in St. George, no?
Depends on the program you're in, honestly.
Oh, okay.
Some programs are more laid back than others. Okay, so this is our last page, and then we're probably gonna take a break. I honestly don't think we're gonna get through the division lesson because we're not gonna have enough time.
It's fine. Like 40 minutes isn't enough. Not that
This took me a full period to explain, and you guys didn't even have extra work or extra time to do your homework.
I'm-
I don't know. Some of these lessons are pretty long. Okay, so this one's pretty easy. So for example 1, we're going to determine the degree of each polynomial. So what is the degree for 2a? Or I mean for example A.
14.
The degree. You don't add them. Remember, it's just the highest. You only add them when it's in expanded form.
You mean fact?
In factored form, sorry.
Oh, okay.
In expanded form or in standard form, it's just the highest degree. So what is our degree for this polynomial function? 6.
See, does that mean, so if it's in factored form, right, for B, the degree would obviously be 4, because if you expand it, it would be like, you know, the 4 would be the highest. Okay.
So what is our degree for B? Jose just said it.
Sorry, I
4.
was trying
That's
to.
fine.
What if it's not like fully expanded, so like you have to like expand it more, and then you can count, or is it just like whatever's in brackets?
So you'll always have it like this or in this form.
Like maybe like a factor, like what if it like you can still like expand it more, and you just like go off like what?
Oh no, don't expand it more because then you're just gonna
Just
have
like
more work.
leave it as-
Yeah.
okay.
So for C, remember the definition, it has to be a positive exponent, right? If we bring this back up, our exponent becomes what?
Negative.
Negative. And therefore, there's no degree for this one.
Yeah, that's not what's falling.
No degree because it's not a polynomial function. Okay, so for example 2, we want to classify each function. And we want to state the degree and the leading coefficient of each polynomial. Okay, so what type of function do we have in A? Central. So this is a trig function. All right. What type of function do we have in B? Cubic, quintic, quartic. Okay. What is our degree? Degree is 4. And what is our leading coefficient? What's the number in front of the x? Positive 2. Okay. The next one, what type of function is it? Cubic, which means our degree is what? And our leading coefficient is? Positive 1. Okay. The next one, what type of function is it? Okay, there's no real degree to it. Okay, and then the next one, quartic. What's our degree? 4, and our leading coefficient? Positive 3. The second last one, quartic again. Degree is 4, and our leading coefficient is what? Negative 1. And last but not least, what type of function do we have? Square root. Remember, it has to be a whole number, so is there a real degree for this? No. Because the degree is just 1 over 2. And then we have our last example, or second last example.
Sir, is there no leading coefficient for?
No, it only says that you can state the leading coefficient and the degree if it's a polynomial function.
So you don't need it for the ones that are not polynomial functions. So example 3, we want to describe the end behaviors, the number of turning points, the number of zeros, and we want to use these characteristics to sketch the possible graphs of these functions. Okay? So what is our degree for the first one? For A? 5. So what is our leading coefficient? Negative 3. So does that mean our graph is opening up or down? Down. So because it's an odd and it has a negative leading coefficient, what quadrant is it starting at and what quadrant is it finishing?
Starting at 3, finishing at 4. Wait, sorry. Actually, I have no clue.
Just Joseph.
Starting at 2 and ending at 4.
So from Q2 to Q4.
Oh, because it's odd?
Yeah, because it's odd. So how many turning points can we have? Number n minus 1. 4. How many x-intercepts can we have? Look at the degree. 5. And what would our n behaviors be? Remember, look back at the note you wrote. If we have a negative leading coefficient with an odd degree polynomial function.
X approach is negative, infinity, y approach is negative. Or y approach is positive.
Positive infinity.
Why is the x intercept 5?
Because remember, we can have 5, this can be factored into 5 distinct separate brackets. That's why.
Okay, I got mixed up with the y.
Yes. So as x approaches negative infinity, y approaches positive, and what would the other one be?
X approach is positive, y.
So obviously, because we can't factor this yet because we don't have the skills yet, we're just going to draw a rough sketch. Okay. Okay. So that's 4 turning points. The x-intercept, because one is a double root, okay, the parabola, and it satisfies the end behaviors that we looked at before. So that's just a rough sketch. I'm not saying the actual function looks like that. This is just a rough sketch based off what we know and the definitions we looked at today.
Wait, sir, how was that last point? X intercept,
Because it bounces off the x-axis, it touches it.
does such as it.
Oh, so I was listening to my recordings. I hope you guys are okay with hearing yourselves for a bit, like very minusculely. Because I heard some of your voices or whatever.
What's the recording from yesterday's session?
Oh, no, not yet. That's what I forgot to do. Oh, sorry. Hope you guys are finding those beneficial. That way, when I teach this again, I don't have to record again. I'll just say, refer to my last class.
Ours,
This is a good thing about this, is that
it's digital.
it's digital, and that way when we get back to normal, students who are away, I can just refer them to the video, right? So they technically don't miss class, they can just sit at home and just watch it. So the next one, we have a even degree with a positive leading coefficient. So our degree is 4. What is our leading coefficient?
Positive.
Positive 2. How many turning points can we have? 3. X-intercepts? 4. And what would our end behaviors be for a positive leading coefficient even degree polynomial?
As x approaches negative infinity, y approaches positive infinity.
Yep.
As x approaches positive infinity, y approaches positive infinity.
Perfect. So a rough sketch. So you have 3 turning points and 4 x-intercepts. So the last example before we get into long division and synthetic division after the break. We want to illustrate an example of a polynomial function that has the following end behaviors. So as x approaches negative infinity, y approaches negative infinity, and as x approaches positive infinity, y approaches positive infinity. So would that be linear, quadratic, cubic, quartic, or quintic? Cubic? Okay. And just give me the most basic one.
Like, can it be like linear?
Can be linear. Yeah. Can be linear as well.
So it doesn't matter, it's just like an example.
So we can take y is equal to x cubed. All right. So was that easier than the first unit?
Yes.
Because you guys understand it better?
Yeah.
Okay. So this is what it looks like before we actually start factoring and graphing. So the first part of this unit is just looking at the graph and analyzing. The next few parts of the unit are going to be knowing how to factor and knowing how to sketch graphs. Okay. So you guys have 10 minutes to do your homework, and then at 9:40 we will take a break. Okay. And then cohort A and C, you guys can do the same. You guys can don't leave yet, I need to take attendance. So give me 2 seconds so I can take attendance.
Wait, did you not write for double sided?
This is not a double-sided printer.
Oh.
Oh.
This